thanks everybody for being here. I'm going to talk about samarium and lutetium hafnium systematics, specifically in garnets. That's the best mineral for metamorphic rock, not zircons. What I really like about garnet is that we're not just focusing on the age here. We can actually relate the garnet with several petrological processes. So we can look at the garnet textures, quantify pressure and temperature conditions through barometers and thermometers, pseudosections, modeling, Raman, look at stable isotopes, trace elements, oxygen isotopes, and then we can all relate it to this characteristics or just characteristics of the garnets to link into petrological processes, but then we can also link this to chronological processes. So using samarium, lutetium, hafnium, both of them, and trying to calculate, for example, the velocity of which some processes is happening by using geochronology, for example. So I'm going to talk about these two systems here. So I'm not getting into details with this. I think too many people talk about it already. But as I said, the importance is just constraining the time of metamorphic events and linking these to different pressure and temperature conditions at a certain time. We can also use samarium isotopes to a range of other minerals, such as apatite, titanite, monazite, and this goes really well with Milo was speaking before with the tridomineral province and also trying to track fluid-related processes, especially in mineralized terrains. But we are more interested in the garnet today. So for the samarium, it works through, we have to collect samarium isotopes through TIMS analysis due to the low availability of samarium and neodymium in the garnet. So we have to do wet chemistry columns, which is this ones here. Yana talked about this a little bit before for lead isotopes. Because we are doing TIMS analysis, these generally have a very high precision, so we have very precise ages. But we also lose a lot of textural control in garnets, which are zones. They can have several petrological complexities, and this is sometimes handled using micro drilling. If the garnet's large enough, you can actually remove parts of the garnet and just analyze different bits of the garnet. If you want to know more about all the samarium teams, garnet geochronology, Kaylee Harvey, she's a postdoc at Boston College with Ethan Baxter that does a lot of samarium, and she has a Twitter thread all about all these stages, which is interesting. And we generally present the data using normal isochrones. So 147 samarium over 144 neodymium versus 143 neodymium, 144 neodymium. And as we said before, like we have to do this by separating the garnet. So it's generally not a lot of points because it's very painful to separate the isotopes through the chemistry columns. And then we just present the whole rock to pin down the initial ratio here, and then maybe 3 or 4, 5 garnets or leached parts of the garnets to constrain the isochron. I'm gonna talk more about study cases to show how we can use the garnet instead of just talking about the systematic itself. This paper by Mark Kadek's PhD student Jennifer, they were looking at a paleo subduction zone in Greece, so in Syros. It's called cycladic blue schist unit, and they used a range of different petrological tools coupled to samarium and geochronology. This is an example of one of the garnets they were looking for. So as I said before, garnets have a lot of complexity inside of it. And because this garnet is actually pretty big, they managed to separate the inner core that they call inner core and the outer ring pretty much with micro drilling to do the geochronology. So they linked this to quartz Raman to calculate the pressure, but also to pseudo-section modeling. I'm not getting into details in why they have different pseudo sections for considering different parts of the garnet. This is just fractional crystallization. We need to consider this for the garnet, but they consider that this garnet, the garnets from the sample, they recorded 2 or 4 stages. So the inner core is 485, 2.2 GPa. The outer core, 530, 2 GPa. And then there is a slight decrease in pressure towards the outer ring that goes to 550 degrees and 1.6 GPa. The inner core, they got an age of 45.3 plus minus 1 million years. So again, it's a really precise age. And the garnet outer ring is 40.5 plus minus 1.9 million years. So just by coupling pressure temperature conditions and very precise ages, they were able to understand how this failure subduction zone was happening. So the garnet just records, or their interpretation is that the garnet it grows in the decompression path. So the garnet core at 45.3 plus minus 1, it takes the original blue schist metamorphism, which was thought to be older before. Well, there are some evidence that in other places it goes to 60 million years or 50 million years. And in the garnet ring is already the decompression of the subduction system at 40.5 plus minus 1.9 million year that they associate with this slab rollback of this subduction. And by using PT conditions and the ages, they are able to calculate exhumation rates. So it goes from approximately 0.3 to 0.7 centimeters per year, and a geothermal rate of 10 to 28 degrees per million year. So that's what I think that it's the beauty of geochronology metamorphic rocks, that we can couple the processes with the ages and petrological events. The lutetium hafnium works pretty much the same, just different isotopes. But in the end of the talk, I will explain why they are both important. I want to highlight here that we have analytical advances towards lutetium and hafnium due to a collision reaction cell instruments, which is the triple quad ICP-MS, which allows us to do the in situ geochronology of garnets, which is, given the whole textural complexity of garnets, is a great advance. This is impressively the first paper using garnet lutetium hafnium published in Nature. So if you try to do this today, you're going to be rejecting 30 minutes. But this paper actually was dating for the first time the high pressure, ultra high pressure metamorphism in the Alps. The geochronology before was really incipient in terms of the high pressure metamorphism. So these authors managed to take 3 samples and then see that the high pressure metamorphism is more like a diachronic processes in the Alps instead of just prolonged single event between 120 and 80 million years. So they made it to Nature. And again, they made it to Nature because at that time, so 97 was really difficult to measure the hafnium isotopes in garnets. How can we do this? We can do this by using multi-collectors ICP-MS, but then again, it needs to go through the whole wet chemistry column separation. It yields more precise ages, but again, we lose a lot of textural control. And as I said before, now we have the triple quad ICP-MS, which allows us to go in situ, which requires much less sample preparation and allows us to have a slightly good textural control depending on the grain size, of course. In this case, we can present the data as normal isochrones, like this diagram here, or just as inverse isochrones, like this diagram. The benefit of using an inverse diagram, and which is the authors Lee and Vermees 2021, they actually recommend to use the inverse isochrones for isotopes when the 177 happening here and here, they are less abundant, you get into extreme error correlations. So this minimizes internal variations of the data. And then when you normalize the data for higher abundance isotopes, which is 176 happening here, you kind of remove the extreme error correlation and you get a base that is a better estimate of the age, which is always a little bit younger. But that's the recommendation. So I'm going to talk a little bit of the triple quality instruments that Hugo's going to talk about it as well. So with the lutetium happening, the problem before is that 176 lutetium, 176 ytterbium, and 176 hafnium, they all overlap. So there's a mass isobaric interferences. With these new instruments, with the triple quad that we already have, and with the NEOMA that we bought, and it's going to arrive first semester next year, we can actually add some oxidizing gas, which will promote a mass jump in the isotopes. So in this case, the hafnium is going to create complexes, and then the mass is going to jump. So it's going to go without any interference to the 176 lutetium and 176 ytterbium as well. So we can actually get a 176 hafnium-free interference using the gas ammonia. And I'm going to present one of my papers to the top of my knowledge. I think it was the first one using in situ lutetium hafnium Garnet as a study case. So my PhD was done in this terrain here. It's called Riwapa terrain in the southwest margin of the Amazon Craton. And through my whole PhD, I probably dated 2,000 zircons. I've never seen one single metamorphic zircon. So in this paper, I was interested in understanding if there was a medium temperature event that were missing, because people just, and myself, missed all of the medium temperature events dating high temperature minerals. So this terrain is part of the Cratonary system developed in the southwestern Amazon during Paleotermesoproterozoic. And the only thermal event that we knew at that time is the 1.2 billion years event that was recorded on potassium argon and argon ages. But what else? Something needs to happen between 2 billion years and 1.2 billion years. And then I thought we were missing something. Just a detail of the map that I was looking for. So I did a transect here, collecting samples from these nice complexes, detritus, meta-sedimentary samples here, and also gneisses from here and So I did a lot of UPB trace elements in different minerals, but today I'm just focusing on the in situ rubidium strontium coupled to in situ lutetium hafnium phase equilibrium modeling. This is the garnets that I was looking at from this unit here, which is a meta-sedimentary unit. So this sample is a simple garnet biotype muscovite schist, but the garnet has a lot of complexity in itself. So there is a massive, pretty clear, it's not a diffusion process here. So there is resorption of the garnet from the core to the rim and outer rim. And by using phase equilibrium modeling, I was able to calculate the conditions of the core, the rim, and the outer rim. So they actually create like an anti-clockwise PT path like this. And interesting enough, the composition of the micas, the muscovite, which is this green band, it kind of overlaps with the outer rim, which allows us to indirectly date the garnet outer rim using in situ rubidium strontium muscovite. So here it is, the muscovite in situ rubidium strontium yields an age of 12, 16, 64 plus minus 18 million years. And the garnets yields an ages of 1334 plus minus 16 and 1348 plus minus 24. So as a summary of my paper, we figured out there were 4 medium temperature events that were missing before. The first one was 1780 million years. The second one was revealed by in situ rubidium strontium in micas at 1625 million years, which is pretty much the closure of the two domains of the terrain. So it's the just juxtaposition of the western and eastern margin. And then using the Garnet modeling and the Garnet geochronology, we figured that we had a high pressure event at 1420 to 1340. And this correlates with the regional tectonics of the southwestern Amazonian Craton. And we figured out that this terrain here, there is actually a high pressure, medium temperature, high temperature, medium pressure, and here is a high pressure, medium temperature. So that's kind of a parametamorphic belt that wasn't recognized before because we are missing the correct techniques to investigate it. So my final remarks here is that garnet, samarine, neodymium, lutetium, hafnium are super important for metamorphic rocks and processes. That's why the best, not certain. Some things that I want to highlight, why or when using samarine, neodymium, or when using lutetium, hafnium, and it really goes to what are you actually looking at, looking for to resolve. First thing you need to have a look is that they have different carrying isotope zonation. So lutetium, it partitions really strongly to garnets, whereas samarium doesn't. So here, a paper from Smith, 2013, we can see this kind of Bell trace element distribution, which is pretty classic of highlight distribution with heaps of lutetium in the core of the garnet. And then when you look at the samarium, it's just kind of flat. This creates a skewed distribution with lutetium being more concentrated in the core. So once you get lutetium, hafnium, garnet ages, it's more likely to correspond to the ages of the core instead of the rims. Whereas when you look at the samarine, neodymium ages, it's more likely to tell you about the processes that are forming the exterior parts of the garnet. When we have papers that use both techniques, we generally get different ages, with the lutetium, hafnium being older than the samarine, neodymium. So this paper is kind of a theoretical paper using different grain sizes of garnets from the same sample. So I just selected two diagrams here. So you, in the same diameter of grain, we have this lutetium, hafnium age of 2711 plus minus 9, and in samarine, neodymium age of 2619 plus minus 13. And this is all related to the distribution of the elements and also to the different temperature, different closure temperature, with hafnium being much slower than neodymium, which causes to have a higher closure temperature. So just, again, this paper by Smith, 2013, they model the theoretical closure temperature for garnet, lutetium, hafnium, and garnet, samarine, neodymium using the Dodson equation. So imagine a closed system, and we can see that for a same diameter, the lutetium, hafnium is way higher than the samarine, neodymium. So once we define the problem that we want to tackle, we can decide which system is more suitable for our study. With the lutetium, hafnium being really good for those people that are interested in dating the core of the garnets, and especially if you have textural complexity and you want to target or try to target this complexity, definitely using the in situ lutetium, hafnium approach. I think for now there's only 2 papers published with 3. Okay, so 3 papers published with this, and there's a lot of space for contributing and publishing cool science. For those interested in garnets, the best mineral, you can have a look at this book. It's a review book called Geochronology, and there is a chapter 15. It describes all the processes of garnet, all the PT stuff, and geochronology. It's really good, recommended. And that's it. Thank you.